Okay, so we just did these frequency tables to organize data. Now the next step, let's look at our favorite color here. And I'm going to use different data just to make it a little more interesting. I'll leave out the tally column. So we're going to go with red, blue, and green again. And let's say that out of 20 people, we had 7 responses for red, 4 responses for blue, and 9 for green. So yes, that does give us a total of 20. There are several things we can do to display this data. I mean, the frequency table makes it a little bit easier to interpret, but it still can be slow. If I want to know which one's the most popular or least popular, I can find it here, but there's only 3 colors. If I had like 10 colors listed, it would be a little slow to find. But I can put them in a graph to make it easier. One type of graph I can make is a bar graph. A bar graph can be done one of 2 ways. I can either have the categories across the bottom here, and some sort of a scale up the side. Now notice I made sure that that went up to at least 9 because that's my highest frequency. Or I could have put the categories on the side here and had a scale going along the bottom. Typically in statistics, we like our graphs going up and down, so I'm going to do it that way. But it is okay to do it sideways, a horizontal. This is what we call a vertical bar graph. It is okay to have a horizontal bar graph. So now red is 7, so I'm going to put a bar above red that goes up to 7, like that. Blue is 4, so above blue I'm going to go up to 4. Green is 9, so above green I'm going to go up to 9. Now, looking at this graph, I can very quickly pick out that green was the most popular, blue is the least popular. And if I wanted to compare two, like if I wanted to compare red to blue, I can very quickly see that red has more than blue. Now, because these are relatively small numbers, it's also pretty easy to see what number. I mean, red is 7, blue is 4, green is 9. But typically that is one of the weaknesses of a graph, is finding exact numbers. If I wanted to do sales for large corporations, and I'm just going to go corporation A, B, and C, and I'm going to put this one sideways just to show you what a horizontal graph looks like. But let's say this is in hundreds of millions of dollars. Here's A, B, and C. Companies A, B, and C. Well, it's very quick to pick out here which company had the highest sales for that period. Not everybody at once. B, okay. Which company had the lowest sales? C. How many dollars in sales did company A have? Well, we trace this down. It's not quite 200. This is 175. Is that 190, 192, 192,347,618? What is it? That's one of the weaknesses of a graph, is you can't get exact. It's tough to get exact numbers from a graph. If you wanted the exact sales, then you'd refer back to whatever table this graph came from, and you'd look at that. Graphs are meant to make quick comparisons. Like I said, find the largest, the smallest, and then compare two values to see which one of those two is largest. When I made this graph here, I did something I shouldn't have. I did it on purpose. Can anybody tell me what it is that I should not have done? I should not have, and there's different arguments on this. Newspapers and magazines do what I did all the time. I should not have made the bars different colors. Why not? Well, because behind statistics, there's a lot of psychology. And different people, their psychology is different. I'm sure you know that. But to different people, different colors draw their attention more. Typically, red is one of them for a lot of people, but not everybody. Red, even if it's similar in size to something, will stick out and appear larger to some people. So here, I made it obvious that there were different sizes, but if the red and green had been close, having the red bar drawn in red might make it look bigger than one drawn in green, even though they're about the same size. So some of that psychology, there's certain things you have to be careful of to avoid portraying something that's not quite accurate or portraying something you don't intend to when you're dealing with these. Often in pure statistics, decorating a graph is very, very sketchy. I mean, there's certain things you can do to make the graph prettier and more attractive and flashier, but there's a lot of things you can do that could possibly be misleading, and that's one of them. Now, on the other side of that, if you get into advertising, one of the points in advertising is try to use statistics to sway someone to a certain side, or in politics even. So a lot of times this is done intentionally to try to pull somebody in a given direction, to try to literally be misleading with your statistics. For example, this example I just did down here with the companies. I'm going to do a similar example. Spread them out just a little bit more. These, once again, are all sales in hundreds of millions, or in millions of dollars per period. So this would be 250 million, this would be 300 million. Looking at this, if you're going to compare company B to company C, how many of you would say company B had twice as much sales as C? Okay, you caught the fact that the graph does not start at 0. Company B does not have twice as much sales as C, but if you weren't paying attention, it'd be very easy to say, hey, that's twice as tall, it's twice as many sales. And it looks that way. Even if you do see the scale, it still looks that way. Now, graphs like this is called a broken scale, are done sometimes with the best of intentions to try to highlight the differences so you can see them better. But it's also possibly misleading because, like I said, company B looks to be twice as tall as company C. If I had done a graph like this without breaking the scale, probably could have expanded it a little bit more than that, but that's what the graph would look like without having the broken scale. You can see all three companies are very, very close in sales. So one of the biggest things I want to point out to you is potential misleading uses of statistics as we go through this. This is one of them. Graphs. There are a lot of things that can be done on graphs that make them potentially misleading. So that's bar graphs. Another type of graph that's often done with categorical data like this involves using the relative frequency mostly. In fact, usually it's the percent frequency, so we're going to make the percent frequency. So 7 divided by 20 is 0.35, so that's 35%. 4 divided by 20 is 0.20, so that's 20%. And 9 divided by 20 is 0.45, so that's 45%. Again, those better come really close to adding up to 100. I can display that data on a circle graph. Now, once upon a time, to make a circle graph, what we would have done is we would have taken, how many degrees are in a full circle? 360. We would have taken 360 degrees. We would have, for the green, we would have found 45% to get how many degrees that is, and then use a protractor to measure out that many degrees and make our graph. Well, now if we want to be that precise, there are literally dozens of free computer programs out there, or cheap computer programs that will do that for you, to be exact. So for our purposes, sketching it out by hand, we're going to go off of just, we mentioned before, benchmarks. Half a circle is what percent? 50%. Quarter of a circle would be 25%. Half of that would be 12.5%, right? So I look up here, I have 2% that are relatively, 45% is just a little bit less than half. That's my green. 20% is a little bit less than 20, or 25, so I'm going to put that there. That's my blue. The rest of this must be red. So there I have a pretty precise graph. I mean, it's not like exact, but it's close enough. You can definitely see that blue's the smallest, green's the largest. And that green is just slightly less than half. One type of graph I am going to show you but warn you against. This is one of those graphs that is very, very popular in advertising, very popular in magazines because, well, it's attractive. It's flashy. It makes a nice little picture. It's also very, very highly potential to be misleading. Picture graphs or pictographs. For example, let's talk about transportation to work. Most picture graphs have a key. So let's say that walking to work, one little person equals 4 people that responded that they walked to work. What's that mean? Half, yep. So 1, 2, 3, 4 times 4 would be 16. That looks like it's probably about 18. Again, that might be a fourth of a person, who knows. Biking. Let's say one little bike equals 10 people. How many would you say that is? We know it's more than 20. 22, 23, somewhere in there, yeah. 2 1/4. We know it's between 20 and probably a little bit less than 25, right? For cars, for driving, that's 20. Well, each of those is 20. It says 20, 40, a little bit less than 60, right? Who knows where exact. For bus, there's some other bakery truck. Oh well. So that's 30. How many would you guess that to be? Well, again, just under 60, right? But one thing you'll notice here is it doesn't necessarily go to scale. The cars and the buses are both of them are just under 60, but they don't necessarily come to the same point. And pictographs can be very and you also see up here, you see 4 people, 4.5 people compared to only 3, almost not quite 3 cars. Your mind wants to say, hey, there's more up here. Pictographs can be very misleading. Another thing that can be misleading about pictographs would be this. Let's say I want to compare company A to company B again. I want to do their sales again. I might do this. If I were to compare company A to company B, obviously company B is larger, but by how much? Well, really, all that's being measured here is the height of the top of that front box. The depth means nothing, but the exaggerated depth and width on this one makes it look like it's like 4 or 5 times the size or more. They pass these off as bar graphs. They sometimes call them 3D bar graphs, but it is a form of a pictograph. And again, they can be misleading. You kind of get a common theme going through here. Things can be misleading. You have to be careful how they're represented. And when you read them, you have to be careful how you read statistics. Now, the next type of graph is a little bit different. What we've looked at up here for the data, the categorical and the numerical, is all snapshot data. It's a single moment in time. We've taken measurements and we've displayed different variations, the amount from different variations. What we're going to look at next is something called time series. What time series is only measuring one variation or one possibility measured at different points in time. So you might look at school tuition. And let's go over 5-year periods. So let's say that in 1995, 2000, 2005, 2010, and 2015. So this is obviously the year. This is going to be the dollar amount. Let's say in 1995 is $89 per credit. In 2000, $98 per credit. 2005, it went up to $134 per credit. 2010, it dropped to 131, and in 2015, it was up to 144 per credit. So if I'm going to graph this, I'm going to use what's called a line graph. And a line graph represents the changes in this value over time. Time will always go across the bottom line here. This will be 1995, 2000, 2005, 2010, and 2015. And again, I have to make sure my scale goes up to at least the largest value of the data. 1995, it was at 89. It would have been somewhere in here. 2000 was at 98. Be somewhere in here. 2005, it jumped up to 134, which is somewhere in here. 2010, it dropped down just a little bit to 131, and 2005 up to 144. So we connect these dots to make our line graph. Now there are two very powerful things in the line graph. One, as you can tell whether things are increasing or decreasing. Looking up here, there's only one period of time where it was decreasing, and that is 2005 to 2010, because the line's sloping down. You can also find where it's increasing or decreasing the fastest. Where did it increase the fastest? Yeah, because it's the steepest between 2000 and 2005. That's where it was increasing the fastest. Now, between 95 and 2000 and 2010, 2015, those lines are really close to the same slope. It's really tough to tell. It actually was slightly faster from 2000 to 2015, but close to the same. So again, there are some weaknesses. You can't get, if they're close, you can't get an exact difference between them from the graph. You have to go back to the table. These all look familiar? Okay. Now there is something out there that can be done. You use the time series to compare over several different points in time. Sometimes used to compare either two different points in time or maybe two different companies or whatever. Something called a double bar graph. So what I'm going to show here is sales for a single company. What I'm going to show is first quarter, second quarter, third quarter, and fourth quarter. (2014, 2015) for each quarter. Now here a lot of times they will use different colors. So I might use, here's 2014, first quarter sales, 2015 first quarter sales. 2014 first quarter sales, 2015 first quarter sales. Second quarter, third quarter, 2014 third quarter, 2015 third quarter. And then fourth quarter for 2014. Can anybody tell me why fourth quarter would be so much higher? What happens during the fourth quarter of the year? What's that? Christmas. Retail sales are always highest in the fourth quarter. That's why a lot of your stock, most companies do their sales projections and stuff like February, March, because that's they can figure out what their holiday season was. So now here you can very quickly compare. In the first quarter of the year, we did better in 2015, but every quarter after that, it was either slightly worse or close to equal. And so it allows us not only to compare different things, first quarter, second quarter, third quarter, fourth quarter, but it allows us to compare between the two different years as well. I know I didn't put a scale here, but I'm being a little lazy right now. Okay, so we've gone from displaying our data graphically. I'm going to end this recording, and then we're going to talk for a little bit about starting to basically summarize our data numerically.